In this slide, I want to cover an important property of the discriminants. So just a reminder, the discriminant d was, so given a quadratic ax squared plus bx plus c, so given a quadratic ax squared plus bx plus c, its discriminant d was this expression, b squared minus 4ac, the expression that participated under the radical in the formula for the solution of the quadratic equation. So that number d equal to b squared minus 4ac has some special properties. Let the roots of the equation ax squared plus bx plus c, let those roots be x1 and x2. So x1 and x2, they were given by some complicated formula. If you remember x1 and x2, those were minus b plus or minus radical of b squared minus 4ac over 2a. So these one of these guys with the plus is x1 and the other one with the minus is x2. And so what does this slide say? Well, it says, look, if you take b squared minus 4ac, so if you take that expression, b squared minus 4ac, take that expression, then you get the same thing that you would get if you take x1, take x2, subtract the two, square the whole expression and multiply it by a squared. So you can obtain the discriminant using x1 and x2. So that's what the proposition says. Let's quickly prove that proposition. So in order to prove the proposition, we need to start with the expression a squared times x1 minus x2, the whole thing squared, right? So that's how we start. And we need to demonstrate that that expression that we see over here, a squared times x1 minus x2, the whole thing squared, we need to demonstrate that this expression is equal to d. We need to show that that expression is equal to d. So the expression a squared times x1 minus x2 squared, that is of course equal to a squared times, so let's see, so this is my x1, right? x1 is minus b plus radical of d over 2a. And my x2 is minus b minus radical of d over 2a. So there we go. So let's simplify. Now these two fractions have the common denominator. The denominator repeats. So what's in the numerator can be put together. So I'm having here minus b, and here I'm having minus b. So minus b, that is plus b, and plus b minus b, the two cancel. So I can cancel the minus b here with the minus b there. Okay. So now, here I'm having plus radical of d minus radical of d. Minus with minus gives me plus. So I'm having radical of d over 2a minus radical of d over 2a. But that's radical of d over 2a. Minus and minus gives me plus, so plus radical of d over 2a. And then I can bring those two on the common denominator to get radical of d plus radical of d over 2a. It's just common denominator, and radical of d plus radical of d is of course equal to 2 times radical of d over 2a. So that's what I get. The 2's of course cancel. 2's cancel. Now, when I square radical of d, I get d, right? So radical of d squared, that's equal to d. Just a reminder, this always holds, right? So the other way around, there was trouble. So radical of d squared, that was plus or minus d. But when you have radical of d then squared, then you always get d out. Even if d is negative, if you go through the complex numbers, when d is negative, this always holds. So no problem there. So radical of d squared, that's equal to d. a squared is, well, a squared, and now the two copies of a squared cancel, and we get d. So let's recap. We demonstrated with a series of equivalent transformations that a squared times the difference of the two roots squared is equal to the discriminant as desired. This shows that the discriminant of a quadratic equation is 0 if and only if the quadratic has non-distinct roots. So if x1, so the discriminant is 0 if and only if x1 and x2 coincide. So once again, discriminant is 0 if and only if the two roots are actually the same root. In other words, the discriminant discriminates between the two roots, and that actually explains why this d is named the discriminant.